Okay, everybody, we're going to go ahead and get started. This is exponential functions and their graphs. This is lesson 3.1. What I want you to do right now is I want you to make sure that you've got a scientific calculator close by, and you can use the one on your phone or your computer, but you want to make sure it's scientific because you're going to have to be able to take things to a power that's not squared and not to the third. So you need some kind of function that allows you to have an exponent that's not just squared. You might also have a key that looks like that. It's the caret top. So either one of those would work, but you've got to have some key similar to that. The other thing that I want you to do is I want you to make sure that you've got Desmos pulled up on your phone or your computer. So if you don't have those close by, go ahead and pause for just a second and then run and go get those and then come back to finish listening to the video. Okay, here we go. What we're going to be doing today is we're going to recognize and evaluate exponential functions. Then we're going to graph the functions. And then we are going to solve some equations with those. So we're going to have a couple different bases. So what we want to do first is we really want to talk about what is an exponential function. What is an exponential function? Now, we've talked a lot about polynomials. We've talked about linear functions. We've talked about quartic and cubic functions. And all of those have a very nice whole number as your exponent. And we're going to move into looking at things a little bit differently. An exponential function is when your unknown is in the variable. Okay, so this is a to the x power. And a couple of things are happening here. Our a value has got to be greater than 0. Okay, now it could be a fraction and it could be a decimal, but it has to be greater than 0. So our base cannot have any negative numbers. So no negative numbers for our base. Okay, and that is this right here. Our a value cannot be negative. Also, our a value cannot be 1. Okay, it can be less than 1 and it can be greater than 1, but it can't be 1 because 1 to the first power, 1 to the second power, 1 to the third power, we're just going to keep getting 1. So for something to be an exponential function, we have to have a base that's positive and our a value can't be 1. Now, x is our unknown. X is our exponent right here. X is any real number. So it's okay for our exponent to be negative. Our base cannot be negative, and that's the number that we're raising to an exponent. But it is okay if our exponent is negative. So it is okay to have a negative exponent. Okay, here are a couple examples of exponential functions. We have f of x equals 2 to the x power. Okay, another one is f of x equals e to the x plus 1 power. And e is a very special base that we'll use a lot during this chapter. So we'll talk more about e soon. So let's start evaluating a few exponential functions. Okay. You're used to doing some when we've got whole numbers. So I want us to look at 4 to the third power. Okay, 4 to the third power. And we know that that means 4 times 4 times 4. 4 times 4 times 4. And 4 times 4 times 4 is 64. Okay, 4 times 4 times 4. Now, we have done just a little bit with 4 to the 1/2. 4 to the 1/2. 1/2 actually means square root. So 4 to the 1/2 is the same thing as the square root of 4. So our answer to that one is 2. Now we'll talk more about this. This right here is called a rational exponent, and that means fraction. Okay, so we have a fraction for an exponent. Now, up until this chapter, we've always used whole numbers as our exponents, and we kind of might have used a negative exponent every once in a while, but we haven't talked a ton about fractions. I know we've used it maybe once or twice, but now our fraction can be any real number, and that includes fractions and decimals. Now what I want you to do is I want you to grab your calculator. So grab your calculator, and we are going to do 2 to the x power on our calculator, and our x value is going to be negative 3.1. So I want you to do this with me, just like being in class. I want you to take and these are the keystrokes for your calculator. You're going to take the 2, so you're going to push 2. Then you likely have a button that has a caret top right there. Okay, so it's 2 caret top, and then I want you to put in parentheses negative 3.1. Okay, so we are evaluating this exponential function right here. 2 caret top negative 3.1. Now, if you don't have this caret top button right here, you should have a button that has, it might be a to the x right there, or it could be y to the x. It could be something where you've got this x right here. That's what that button will be like on a scientific calculator. Okay, and so then if you had either one of those, you would push that button instead of the caret top. Now, when we get our answer here, we are going to get an answer that has to be rounded. So when I have 2 caret top negative 3.1, I get 0.1166291. Now I'm going to put a little star right here. You have got to pay attention to how many digits we are supposed to round to. Okay? Pay attention. Pay attention in WebAssign. Pay attention to quiz directions. How many am I going to round to? Very often, it'll be 3 or 4 place value positions. So this is the 10th place, this is the 100th place, and this is the 1000th place. Okay? So we're going to round this to 3 decimal places. So if I tell you we're going to round this to 3 decimal places, I am going to go to the 4th number. If that number is 5 or greater, it tells this number to go up. So when I round this, I am going to have 0.117. 0.117. Okay? And so if you need to pause this and go back and do that again, I want you to do that. Okay? Now, the next one that we're going to do is we are going to do 2 to the negative x, 2 to the negative x power, and we are going to plug in 3. We're going to plug in 3 for that. Now, so for this one, I would not use your calculator on this one. I'm plugging 3 in for x. Notice that negative is in front of that x. That negative stays. So I'm actually going to have 2 to the negative 3 power. 2 to the negative 3 power. And if you remember from Math 131, 2 to the negative 3 power, what that means is 2 goes to the denominator. So I have 2 to the 3rd in the denominator. So my final answer to this one is 1/8. 1/8. Now, the last one that we're going to practice is we're going to have a decimal for our base, 0.6 to the x power, and we're going to plug in x equals 3 over 2. X equals 3 over 2. Now, your keystrokes for that, we're going to have 0.6. Okay, and then you're going to have your exponent button. And remember, if you don't have the caret top, it may be a to the x or y to the x. That's the button that you're looking for on your calculator to raise something to a specific power. Then I want you to put in parentheses are our friend, 3 over 2, or 3 divided by 2. Now, when we get that, after we do that, we get the number 0.4647580. Okay? Now we're going to round to 3 decimal spaces. So that's 1, 2, 3 spaces. We're going to round to 3 spaces. So I go to the 4th number, and that's greater than 5, so it tells that to go up. So my final answer here is 0.465. Okay? And that is evaluating exponential functions. Okay. Before we get into the graphs and before we get into some other stuff, I want us to do a review of some of our exponential properties. And we're not going to do a ton of stuff with this, but our logarithmic properties parallel this. And so I think it's a super good idea for us to review some of these. Okay, now these are exponent properties. If you took 131, we did a lot with exponent properties last year. If you didn't take 131, then hopefully you remember it from Algebra 1 and Algebra 2. So the property that we're going to talk about first is the product of powers. And what that means is if I have a product and I am multiplying 2 exponents together that have the same base. They have the same base. So x to the a power times x to the b power, the same base. This doesn't work if they don't have the same base. Okay? I add those exponents together. So that's a plus b. My key word here is add. And that's going to come up again when we do logarithmic properties. So these are going to very much parallel each other. So if I have x to the 3rd power and I am multiplying that times x to the 4th power, notice the base in both of those is x. That is going to be x to the 7th power. Okay? So that is a product of powers. Now, our quotient of powers is going to be when I have the same base and I am dividing those 2 bases. So I have x to the a power divided by x to the b power. When I have that, and they are the same base, then I subtract those bases. Okay? So my key word there is going to be subtract. Okay? Subtract. So if I have x to the 5th power over x to the 2nd power, so I'm dividing, that is going to be x to the 3rd power. Okay? I subtract. Now, a power of a product, that is when I have 2 things inside parentheses and everything inside the parentheses is raised to a power. Okay? Now, this is not the distributive property, but a lot of students think about this the same way that we think about the distributive property. That a belongs to everything inside that parenthesis. So my x is being raised to the a power, and my y is being raised to the a power. Now, it must be multiplication. It must be. Product means multiplication. And that a belongs to both of the things in there. If there's a plus sign or if there's a minus sign, it doesn't mean that anymore. It's no longer a power of a product. You're raising a binomial to a power, and we have to FOIL. So make sure that's being multiplied. One of the things that happens with this is students forget to give that exponent to the number too. Okay, so if you've got a number inside these parentheses, that number is being raised to the third power as well. So this would be 2 to the third power, x to the third power, and y to the third power. Okay, and that 2 to the third power actually becomes 8. Okay, 2 times 2 times 2 is 8. Okay, power of a quotient is very similar. If I have x divided by y, and I am raising that to the a power, that a is going to belong to the x, and it belongs to the y. Okay, so we have to give whatever's outside to everything there. And again, be sure if you've got a number there that you're doing that for the number also. So this would be 2 squared over y squared. So 4 over y squared. Okay, power to a power. Okay, the key word here is going to be multiply. What we are doing here is we are raising a power to another power. So if I have a to the x power, and I am raising all of that to the y power, then I'm going to multiply those two powers together. Okay, so if I've got a, let's not use a. Let's use something other than a. Okay, let's use x. Sorry about that. Okay. We're going to do x to the second power, and I am going to raise that to the third power. So that is going to be x to the 2 times 3, and that is x to the 6th power. Okay. Now, what happens is this right here is often used with these. So very, very often you're going to have a power to a power with a power of a product or a power of a quotient. Those properties are used together a lot. So be aware of that. Be aware that you're using some of those at the same time. Now, our 0 exponent is anything raised to the 0 power is 1. Anything raised to the 0 power. So if I have x to the 0 power, I get 1. If I have negative x to the 0 power, I also get 1. But I want you to look at the difference between negative x inside parentheses to the 0 power, and I want you to look at negative x to the 0 power. Because the answer to this second negative x to the 0 power, when I have no parentheses, is negative 1. Okay, and let's talk about why. Let's talk about why. The only thing that's being raised to the 0 power right here is that x. X is being raised to 0 power. So when x is raised to 0 power, I get positive 1. But we have this negative 1 right here. That negative 1 is not being raised to 0 power, and that's where I get that negative from. If you look back to our negative x inside the parentheses, all of that is being raised to the 0 power, the negative and the x. And that's where you get your positive 1 from, right there. So that's a little tricky. So just be sure you understand the difference between these two. Okay? Now, negative exponents are very small numbers. They're very small numbers. Okay? So if I have a negative exponent, and if I have x to the negative a power, what that means is I move it to the denominator. This is not necessarily a negative number. It's just a very small number. Okay? It moves to the denominator. So if I have x to the negative 3, That's going to be 1 over x squared. Or x to the third. I'm sorry. It's going to be 1 over x to the third. Okay? Move that up just a little bit. Rational exponents are fractions. Okay? They're fractions, and you're going to use radicals. You're going to use radicals when we have fractional exponents. So if I've got y to the a over b, that's a b right there, y to the a over b, that means I have y to the a power inside the radical, and the b is the root of that radical. Okay? So this right here goes in the inside. And this right here goes in the outside. Okay? So if I have x to the 2/3 power, that means x squared is inside the radical, and then I am looking at the cubed root. Okay? Okay. Now, I just want to do a couple with those rational exponents. I know that sometimes that can be confusing, so I want to do just a couple with those rational exponents. So, let's look at these. Okay. So, my rational exponent right here is a to the c over the d. Okay? A to the c over d. My base is going to stay the same. Do you see that a right there? That a stays the same. Now, the c, which is my numerator, that's what is the exponent inside the radical sign. Okay, so the numerator stays on the inside. The d is what is the index to the radical. So a to the c over d, a to the power c over d, is the same thing as the d root of a to the c power. Now, sometimes it's more complicating when we're using these variables. So let's look over here at the x. I have x to the 2/3 power. My x goes inside my radical. My numerator, or my 2, stays with that x and goes inside the radical. The 3 is my denominator, and it's my index. So x to the 2/3 power is the same thing as the cubed root of x squared. Okay. The most popular one, the one that you will see the most often, is 1/2. And 1/2 is just square root. So our y here goes inside the radical. We do not have to write the 1. The 1 is assumed, and we don't have to write the 2 because the 2 is assumed. It's because we do it so much. So y to the 1/2 means the square root of y, and you actually do not have to have that written out, because if you've got just a square root, it's assumed as a square root. Okay? So let's solve a couple of these. 64 to the 1/2. We just talked about 1/2, and 1/2 means square root. So I have the square root of 64. And if we take the square root of 64, that's going to be 8. Okay? Now, 8 to the 2/3. That means inside the radical, I'm going to have 8 to the 2nd power, or 8 squared. Then I'm going to take the cubed root of that. 8 squared is 64, just 8 times 8. And the cubed root of that is 4, because 4 times 4 times 4 is 64. So 8 to the 2/3 power is 4. Okay? And the last one, we've got the square root of 9. And we already know that 9 to the 1/2 means square root. And so we've got the third power right there. Okay. That was kind of a review of some different things that we did when we were in 131. And actually I say that and I've got one more thing I want us to review. Okay, let's review this before we move into exponential graphs. So this is, all of these have negative exponents. And when we have a negative exponent, we're moving it to the denominator. So 5 to the negative 1, or negative 2. Sorry about that. For some reason, I've got my phone ringing. 5 to the negative 2, what that means is 1 over 5 squared. 1 over 5 squared. Okay? And 1 over 5 squared is 1 over 25. So 5 to the negative 2 means 1 over 25. Now, for 7 to the negative 2, it's already in the denominator. So we are actually going to move it to the numerator. So 1 over 7 to the negative 2 becomes 7 squared. And you can put that over 1 if that makes you more comfortable. And 7 squared is 49. Okay? Now, 27 to the negative 1/3. And I've seen this a lot in calculus lately, so you definitely want to kind of pay attention to this. 27 to the negative 1/3. We want to do this in steps. We're going to take that 27 to the negative 1/3 and we're going to put it in the denominator. So I have 27 to the 1/3 in the denominator. Then I'm going to deal with that fractional exponent. So I have 1 over 27 to the first power, and I can write that first if I want to, but I don't have to. And then I am taking the cubed root of that. The cubed root of that. Now, I can take the cubed root of 27, and it's 3. And the reason it's 3 is because 3 times 3 times 3 is 27. Okay, now we've talked quite a bit about the squares, but let's just take a second just to make sure we've kind of knows what some of our cubes are. So if I've got 1 cubed, that's going to be 1. 2 cubed is going to be 8. That's 2 times 2 times 2. 3 cubed means 3 times 3 times 3. That's 27. 4 cubed means 4 times 4 times 4, and that's 64. 5 cubed is 5 times 5 times 5, and that's 125. And I actually don't have any more memorized. 6 cubed is going to be 6 times 6 times 6. And 7 cubed is 7 times 7 times 7. 10 cubed might come up because that's going to be 1,000. 10 times 10 times 10 is 1,000. But as you can see, numbers get big very quickly when we're dealing with cubing numbers. Okay, so now we've kind of reviewed some of that stuff. So let's look at some graphs. So go ahead and grab Desmos, because Desmos is our friend. And it's good for you to be able to punch some of these things in Desmos. Okay, so grab your computer, grab your phone. You can go to desmos.com. You can use the app. Lots and lots of different options. But let's do that. And what we're going to do first is we're going to look at we're going to graph these two in the same coordinate plane. Okay. We're going to graph this in the same coordinate plane. So if you're on Desmos, and you can do different colors, the first thing that you're going to do is you're going to do 2 caret top X. And you can do that on your keyboard. You can do just 2 caret top X on your keyboard. And once you've got that plugged in, it should look like 2 to the X once you've got it typed in there. Okay? And then the next one you're going to do is you're going to do 4 caret top X and that's going to be 4 to the x once you've got it typed in. Okay? Now, I want us to look at what those two graphs look like. Okay? So here we go. Now, I know this isn't on Desmos, but a lot of my other graphs will be on Desmos. Okay. When we have exponential functions increase very quickly. Okay? So I have a whole number right here. I have 4 and I have 2. Okay? So I am doing 2 to the first power, 2 to the second power, 2 to the third power, and then I'm doing 4 to the first power, 4 to the second power, and so on. And when I do that, it goes up very, very quickly. The whole COVID-19 models, all of them are based on exponential functions. When we talk about flattening the curve, what we're trying to do is get a small number right here that's spreading. So the higher the number, the quicker it spreads. So if I've got 2 people spreading the virus over a period of time, it still spreads pretty quickly, but it spreads slower than if I've got 4 people. Now we're talking about 4 people per 100 or 4 people per 1,000, but this is where those models come from. When you look at flatten the curve and you look at the different things that are published by the CDC, we're talking about exponential models. That's what we're talking about. Okay? Now, I want you to pay attention to the behavior of the graph down here. These are negative exponents. These are negative exponents. Okay? I want you to notice that my graph never crosses in to negative y values. I never cross below my x-axis. When I plug in a negative value for my exponent, it makes my numbers very small. Okay, it makes my numbers smaller. They get smaller and smaller and smaller, but they never become negative. They never cross down into this area. Okay? Now, my 4 to the x power is increasing quite a bit faster than my 2 to the x power. They're both increasing, and they're both increasing quickly. But because I have the bigger base, this function is increasing faster. Okay? Let's look at some transformations of these graphs. You can put these into Desmos if you like. I have f of x equals 2 to the x, and then we're going to move this around. Now, when we are talking about these functions, it's very, very important that we think about what is happening when x is 0. When x is 0. So the red is my parent function right here. This is my parent function. Okay, and you can identify the red function on my graph. You see that red function right there. Now, if I plugged 0 in for x, so if I have 2 to the 0 power, I am going to get 1. Anytime I have a parent function and I am raising a base to the 0 power, I am always going to get 1. Okay, so this point right here, 0, 1, that is the point to watch. When we start doing our transformations, that is a super, super important point to see where it goes. What's happening to it? Point to watch is that 0, 0. So my parent function, every single parent function I'm going to deal with, it always goes through the point 0, 1. Okay? Now, I want us to look at my blue function. My blue function. Now, what we know when I have numbers with my x, okay? When I have numbers with my x, I know that it is going to move right or left and it is going to move in the opposite direction of the sign. Okay, so I should be looking at, this is an x plus 1, so I should be looking at movement to the left 1 space. That's what I should be looking at. So I want you to look at that point 0, 1. That's the point to watch. This point moved to the left 1 space. That's what happened right there. That point moved to the left 1 space. You've got to keep an eye on what is that point 0, 1 doing. Now, here, for my next one, okay, I am looking at what happens away from the x. That 2 to the x power, that minus 3, that is going to be dealing with my up and down movement. Up and down, and it is true to value. Okay, so we should be looking at down 3 spots. Now, the point to watch is not 0, 0. We're not looking at 0, 0. We are looking at 0, 1 because my parent function crosses at 0, 1. This point 0, 1 moves down 1, 2, 3 spots. Okay? So, when we are looking at exponential functions, you want to pay attention to what happens to this point 0, 1. Okay? Does it move up, down, left, or right? Now, I'm going to erase this, so pause it if you need a little bit more time to write that down. Okay. Now, what I'm going to do now is I want us to talk about the domain. Okay, we're going to talk about domain. Now, domain is always your x values. You're always looking at what input am I putting in to my function. What values can I put in for x? Okay, and we talked and we realized x can be any number. Okay, so my domain for this function right here is all real numbers. And that's going to be true for all of these. Okay, I can put any number in for x. So my domain for my blue function and my green function, they're all real numbers. My domain is. Now, my range is what values of y I end up having. And I want you to notice that for my red function approaches 0, but it never, ever, ever, ever touches 0. Okay? So I am talking about this part. When I'm talking about range, I'm talking about my y values. Now, I don't have any values down here for my range. I have none. I start at 0. Now 0 is not included because I never ever touch 0. Okay? And then I go up. So my range is 0 to infinity. Now, the last thing that I want to talk to you about this is asymptotes. Now we talked about asymptotes when we talked about our rational functions. We're going to talk about asymptotes again now. Now, for all exponential functions have horizontal asymptotes. Okay, so when I have an exponential function, I am looking for a horizontal asymptote, and I am looking at the behavior of my graph. Okay, and right now I'm still looking at my parent function, the function in red. And my horizontal asymptote deals with this right here. My horizontal asymptote right here is y equals 0. That means my red graph approaches 0, but it never ever touches it. It never ever touches it. Okay? So that is my horizontal asymptote. And exponential functions only have horizontal asymptotes. They do not have any vertical asymptotes. We're talking about horizontal asymptotes. Okay? Now, I am going to erase this line right here. And I am going to erase this right here. What I want you to do right now is I want you to put this on pause, and I want you to determine the domain of my blue function, the range of my blue function, and my horizontal asymptote of my blue function. So put that on pause, and I want you to do that right now. Okay, we are back. Okay, now for my blue function, I'm looking at my domain. So I'm looking at what values can I put in for x, and I can put anything in it. So my domain for this is the same as my domain for my parent function. It is negative infinity to infinity. Okay? Now, my range is actually the same thing too. It's 0 to infinity because I am approaching this 0 value or this line at 0, but I never ever get there. I don't ever get there. And so my range is 0 to positive infinity, and my horizontal asymptote is also y equals 0. Now, for my green, it is a little different. My range and my asymptote is different. So put this on pause, and I want you to determine for my green, what's my domain and my range and my horizontal asymptote for my green. Okay, put it on pause. Okay, good job. So my domain for my green function is still all real numbers. Okay, and you can kind of tell by the behavior of the graph. This just kind of keeps going and going and going, and it'll continue to get larger and larger, but we can put any value of x in there. Any value that we want to, we can put in there. Now, it's sometimes easier to look at my horizontal asymptote. Now remember, this is the point that we're looking at. This is the point that we're keeping our eye on. And this is my horizontal asymptote for my parent function. Okay? It was x equals, or I'm sorry, it wasn't x equal, it was y equals 0. Y equals 0, and then we have this point right here, 0, 1. For my green function, that 0, 1 went down to 0, negative 2. Okay? And that line, that y equals 0, that moved down as well, and it moved down to right here. Now, we're supposed to move this down 3 spots, and that's what we did with our point 0, 1. It moved down 1, 2, 3 spots, and our asymptote moved down 3 spots. Okay? So my range also moved down 3 spots. So my range for this is going to be negative 3 to infinity. And my horizontal asymptote is now y equals negative 3. Now be careful, because the fact that this point is 0, negative 2 confuses students. And very often students will put that their range is negative 2 to infinity, or their asymptote is negative 2. Okay? But it's not. It's negative 3 because we moved it down 3 spaces. Remember, you started at y at 0, 1, but now we're good. We moved down to 0, negative 2. Okay? Okay, so domain, range, and asymptotes. Okay, well, actually, we just did that. So this is some definition. These are some definitions on what we just talked about. These are definitions on what we just talked about, so you can kind of take a screenshot of that if you'd like. A lot of times students prefer to think about it with numbers. Now, I'm going to show you, and then we'll talk about reflections. Now we're on this side of it, where it's increasing rapidly. Okay? In just a second, we're going to look at what happens when we change this value right here. Instead of having x, we're going to have negative x. And that is going to reflect across the y-axis. When we do that, my domain stays the same, my range stays the same, and my y-intercept stays the same. Okay, all those stay the same, and my horizontal asymptote stays the same. But what I want you to realize is we are now decreasing. We have started up here, and we are decreasing. Now, we are hopeful that the COVID-19, as quickly as it spiked over a set period of time, it will decrease just as quickly. Okay, we don't know when that is, and that's why we're doing our social distancing. But these are the models that the microbiologists are using. It's used in biology, it's used for population growth, it's used for money and all sorts of different things. And so what we're looking at today with the COVID-19 is exactly what we're talking about in mathematics right here. Right, initially, it'll be decreasing just as rapidly. We just hope sooner rather than a long time from now. And so let's look at what happens when we reflect things. And here we go. So this is typically what students like to look at when we start talking about reflections. So my red, what I want you to pay attention to is my red is my parent function. Okay, so here's my parent function. Okay, now what happened is for my blue function, I put the negative with the x. The negative with the x, so it's up here. The negative is with the x, and we reflected across the y-axis. Okay, that's what happened. We reflected across the y-axis. Now, my green function, my negative is in front of the entire function. My negative is in front of the entire function. Look what happened there. We reflected across the x-axis. Okay, we reflected across the x-axis. Now, my parent function, here is the point to watch. When I reflected across the y-axis, it stayed the same. When I reflected across the x-axis, my point to watch, where did it go? Okay, it went to 0, -1 when I reflected across the x-axis. So kind of keep an eye on that. Look at that. Okay, so when you're moving up, down, left, or right, when we start reflecting, our point to watch moves. Okay, once we reflected across the x-axis, this is the point that's now moving up and down and left to right. Okay, now let's talk about our natural base of E. Our natural base of E. So I want you to find your calculator. I want you to look and see where your calculator is. And I want you to find on that calculator a button that says E. Now it may be E or it may be E to the X. Okay, and either one of them are fine, but I want you to push that button. What you need to know about E is that E is an irrational number. Okay? E is not an unknown. We know the value of E. It's an irrational number, very similar to pi. Very similar to pi. Okay? And E is used in a lot of our growth models. It is actually what's being used when you get compound interest, population growth. This is what we're looking at when we're talking about the COVID virus. We're looking at functions with the E in it. Okay? Now, when I raise E to the 0 power, I still get 1. E to the 0 power is still 1. So that is still going to be a point for us to watch. Okay? It's still going to be a point for us to watch. Now, what we're going to do now is we are going to do some computations with e to the x. Okay? And so this is just a definition of your value of e. Make sure you've got that on your calculator. So now what we're going to do for sure, now what we're going to do is we are going to take this function right here, e to the x power, and we are going to plug values in for that. Okay? So the first thing that I'm going to do is I am going to take x equals -2. So I'm going to have e to the x power, and instead of x, I'm going to have e to the -2. So I am plugging -2 in. Now, you can think about that, and we're actually going to compute this, but e to the -2 is actually 1 over e squared. Okay? That is actually 1 over e squared. We're not going to write it like that. We're going to go ahead and do the computation for it, but I do want you to be aware of that. Okay? Now, keystrokes. Keystrokes are important. So what you're going to do is you're going to hit the button, e to the x. Okay? That's the button that you're going to hit. If you have a button that's just E, then you're going to hit E caret top. But you're going to hit one of those computations. I want you to get in the habit of putting your -2 in parentheses. So we have E to the -2. And when you do that, I need to move this over because we're going to get lots of digits. I get 0.1353353. Okay, let me make sure I've got that written down. 1353353. So I'm going to say we're going to round to the third number. So I've got 1, 2, 3. We're going to round to the third digit. I look at this 3. This 3 tells my 5 to stay where it is. So my final answer when I'm rounding to the third decimal place is 0.135. Okay? Now we're going to do e to the -1. So our keystrokes are going to be e to the x. You should have a button that says e to the x, or you can do e caret top, okay, and -1. Get in the habit of putting -1 in parentheses. It's just you're gonna be better off later. When I do that, I get 0.3678794. Okay, I'm going to again round to 3 decimal spots. Okay, the 8 tells the 7 to go up. If it's 5 or greater, I go up. So I have 0.368. Okay, now I want you to go ahead and pause for just a second. And I want you to do the function f of x equals e to the x when x is 0.25 and when x is -0.3. Okay? Put it on pause while you do that. Okay. So now I have e to the x. That's the button that I'm going to push. Then I'm going to put 0.25 in parentheses. When I do that, I get 1,28402. 0.54. Again, we're going to round to 3 decimal spaces. So that means I go to the 4th to determine what I've got to do. I've got a 0. That 0 tells the number to stay the same. So I have 1.284. Okay, and the last one, I'm going to do e to the x. That's the button I push. Then I have negative 0.3 in parentheses. I get 0.7408182. I'm rounding to 3 decimal spaces, so I've got 1, 2, 3. I look at the 8, and the 8 tells the 0 to go up. And the reason for that is because that 8 is 5 or greater. So my final answer here is 0.741. Okay? Now we're going to pop back over to Desmos. We're going to pop back over to Desmos. Okay. So, grab that calculator. I want you to take a second. F of x equals negative e to the x plus 3 minus 4. I want you to determine what is the parent function and what's the movement of the graph. So put this on pause and think about what is happening to that graph. What is happening to that graph? Okay. So, our parent function is going to be e to the x power. That's our parent function. F of x equals e to the x power. Now, what is happening here? What does that negative mean? Okay, so it's not with the x, it's away from the x. The negative means there's a reflection. And the reflection is occurring across the y-axis. Nope, it's not the y-axis, I'm sorry. The reflection is occurring across the x-axis. And it's okay if you plug this into Desmos to see what it does. Your reflection is across the x-axis. Okay? Then I have plus 3. So we have to think about what is the plus 3 telling me to do. And it's telling me to move to the left 3. That's what it's telling me to do. Move to the left 3. Then I have minus 4. And that is telling me to move down 4. Okay? Now let's look at the graph. Let's look at the graph. Here we go. E to the x. Now remember, I've told you this is the point right here to watch. This point right here. That's the point to watch. Okay. Now, when I do the negative, what happens to that point? When I do the negative, my point to watch ends up right here because it's a reflection. Okay? And this sometimes confuses students. So once I do the reflection, my point to watch went from 0, 1 to 0, negative 1. Okay? Now, my plus 3 means I move to the left 3 spots. So I'm going to go 1, 2, 3. So that's my plus 3. And now I'm going to go down 4 spots. So 1, 2, 3, 4. And there's my point to watch. What confuses students is when we reflect. When we reflect, across x-axis, our point to watch changes. Okay, our point to watch moves when we reflect across that. Okay, now if you need to pause or anything to write, to get all this down, you can. What I'm going to do right now is we are going to talk about the domain and the range of my blue function. Okay, we're going to talk about the domain and the range of my blue function. Okay. So we're going to start with domain. We're talking about my blue function, domain. So the domain of lots of my other functions have been all real numbers. Now, it looks like this is going to hit a vertical asymptote, but it's not. For exponential functions, we only deal with horizontal asymptotes. So this right here, it's going to keep going. The closer to negative infinity we get, this graph is going to keep approaching that. We just can't see it because it's so steep. Okay, but I want you to know that that's what's happening. So my domain for this, as with all exponential functions, is all real numbers. I've got negative infinity to positive infinity. Now, this is my horizontal asymptote right here. That's my horizontal asymptote. Now, everything got reflected and then it got moved down. So this got moved down 4 spots. So my horizontal asymptote for my blue function is what it got moved down to. So my horizontal asymptote is going to be y equals -4. That should help us with the range. That should help us with the range of this. Now I'm starting at -4, but this time, because I've reflected, I've gone down to negative infinity. So I actually need to write that the other way. Okay? I have to. When you look at the graphs of these functions, you will see that it passes the horizontal line test. And what that means is that it's a one-to-one function, and so we can find the inverse of that. And we're going to talk in 3.2 about logarithmic functions, which are the inverse of exponential functions. But today we are going to solve some equations. And this property, the one-to-one property, you also may have heard it called the property of equality for exponential functions. Either one of those terms is completely fine. But that allows us to solve some equations. And what that means is, if you've got a to the x and it's set equal to a to the y, because the bases are the same, your x and your y are equal. Okay, so the important thing is, if your bases are the same, your bases must be the same. If your bases are not the same, it doesn't work. So if your bases are the same, your exponents are equal. So look at the example here. I've got 3 to the x equals 3 to the second power. Both of our bases are 3, so our x is equal to 2. So we are going to use that to solve some problems. Okay, and just remember, your bases have to be the same, and sometimes you have to rewrite those bases. And we'll do a couple of those as we work through these. So here's our first one. I have 7x to the x squared plus x power, and that is equal to 4x minus 2. So 7 raised to the power of x squared plus x is equal to 7 raised to the power of 4x minus 2. And because of that property, since our bases are the same, we can do x squared plus x equals 4x minus 2. Okay? So that is how that works right there. And now we solve. And we know how to solve this. So I have, I've got to set it equal to 0 because it's a quadratic. I have x squared. I'm going to pull my 4x over. So I'm going to have negative 3x. And I'm also going to pull my minus 2 over. So I'm going to get plus 2. Okay? So I have x squared minus 3x plus 2 equals 0. I am going to factor that. Okay, I need two numbers multiplied together give me 2, positive 2, and added together give me negative 3. So both of those numbers are going to be negative. So negative 2 plus negative 1 gives me negative 3. Negative 2 times negative 1 gives me positive 2. Now I set each one of these equal to 0. And I solve. So I have x equals 2 and x equals 1. Okay, now you do want to go back and check. It's important that we check these because sometimes we have to throw out an answer. So I am going to have 7 to the 2 squared plus 2 and 7 to the 4 times 2 minus 2. Okay. 2 squared is 4, plus 2 is 6. So I have 7 to the 6th power. 4 times 2 is 8, minus 2 is also 6. Okay, and we want to check both of them. So I have 7, 1 squared plus 1 equals 4 times 1 minus 2. So I have 7 to the 2nd power equals 7 to the 2nd power. Okay. So now we're going to look at rewriting. So what I have here is I have 4x squared minus 23 equals 16. So 4 to the x squared minus 23 power. And it's equal to 16. And that 16 is raised to the 1st power. But our bases are not the same. Okay, I've got 4 and I've got 16. These bases are not the same. But if I can rewrite one of them or both of them so that they do have the same bases, it's a much easier equation to solve. Now, next week we're going to talk about how to solve them if they're not equal. But right now, if you can rewrite them as the same base, you're in much better shape. So I'm going to keep my 4. I'm going to have 4x squared minus 23. And I can rewrite 16 as 4 squared. Okay? So if you can rewrite them, that's what you want to do. So I have 4x squared minus 23 equals 4 squared. So that means that x squared minus 23 is equal to 2. Okay? Now, you may be tempted to just move that 23 over and have x squared equals 25. Completely fine way to do that. So you have x squared equals 25. But when you take the square root, do not forget your plus or minus. Okay? You've got to have that plus or minus there because the answer here is x equals plus or minus 5. So be very careful if you do that because students forget that plus or minus when we take the square root of both sides. The way that I'm going to do it is I am going to move that 2 over. So I'm going to have x squared minus 25 equals 0. And I'm going to do the difference of perfect squares. So when I do the difference of perfect squares, I have that covered. Okay? So I have x plus 5 is equal to 0, and x minus 5 is equal to 0. So I get x equals negative 5, and x equals positive 5. And both of those work. Both of those work because we're squaring it. Okay, so if I square negative 5, I'm going to get positive 25. Okay, and 25 minus 23 is 2. So that works because we're squaring it. Then, of course, if we square the positive, we also get a positive number. And that works as well. So both of these work for this particular problem. Okay. Now, I want you to look at this next problem right here and think about how you might do that. Okay? How might we do that? So what we have is we have 9 to the x plus 3 and 27 to the x plus 6. Okay, 9 to the x plus 3 and 27 to the x plus 6. For this problem right here, we actually have to rewrite both of them. Okay, so 9, we are going to write 9 as 3 squared. And you definitely want to put that in parentheses. So that's 3 squared, and then that's raised to the x plus 3. Now, 27 is 3 to the third power. 3 times 3 times 3. And then 3 to the third power is being raised to x plus 6. Now, this is where students make their mistake. They make their mistake right here. This 2 has got to be multiplied by that x plus 3. And this 3 has got to be multiplied by that x plus 6. So if I had x to the second power, this is a power to a power property, and then x squared is raised to the fourth power, what operation do I do between these two exponents? Okay, we multiply. When you have a power raised to a power, you multiply. So I've got to distribute that 2 and distribute this 3 to those binomials. Okay, so that would make this 3 to the 2x plus 6 and 3 to the 3x plus 18. Okay, now that I have them both written as the same base, I can put them equal together. So I have 2x plus 6 equals 3x plus 18. Okay, I'm going to pull the 3x over. This is linear, so we just got to get the x on one side and the numbers on the other side. So I have negative 1x plus 6 equals 18. I'm going to subtract 6 from both sides. So I get negative 1x equals 12. When I divide both sides by the negative, I get x equals negative 12. Now, that might make you nervous, having a negative 12. But it is okay. It's okay to have a negative exponent. So let's go back and plug this in, okay, to our original problem. So I have 9 to the negative 12 plus 3 equals 27 to the negative 12 plus 6. Okay, so I'm going to have 9 to the negative 9th power, and then I'm going to have 27 to the negative 6th power. Okay, now those are very, very small numbers, because 9 to the negative 9th power means 1 over 9 to the 9th power. That is not 9 times 9. That is 9 to the 9th power. That is 9 multiplied times itself 9 times. It's a 9 to the 9th power is a very large number. And since we're talking about it being in the denominator, it turns into a very small number. So this means 1 over 27 to the 6th power. So I would type that into your calculator. These are the keystrokes. I would do 9, caret top, negative 9. And then I would do 27, caret top, negative 6. And when you type those in, you get a very small number. but they will be equal. They will be equal. Okay? I hope everybody has a great day and a great week, and let me know if you need anything.